सादर नमस्कार, सुस्वागतम, अभिनंदन, केम छो, जय श्री कृष्ण, वणकम, आदावर, सत श्री अकाल, राम राम, राधे राधे, ए वेरी गुड आफ्टरनून। मैं अनिल भारद्वाज आप सभी का पीआरएल के अमृत व्याख्यान के 107वें अध्याय में स्वागत करता हूं, अभिनंदन करता हूं। आई अनिल भारद्वाज very warmly welcome you all to the 107th PRL का अमृत व्याख्यान। We started the PRL का अमृत व्याख्यान as a part of celebration of 75 years of establishment of PRL, which coincided with Azadi Ka Amrit Mahotsav, that is 75 years of India's independence. And it was a tribute and legacy of PRL with respect to Dr. Vikram Sarabhai, who established PRL in the year 1947. He started this with the sankalp that every Friday at 4 p.m., starting from 4th of August 2021, we will have PRL ka Amrit Vyakhyaan. And we continued this uninterrupted PRL ka Amrit Vyakhyaan every Friday, 4 p.m. for continuously 75 weeks. After completing this on 5th of January 2023, we took the sankalp that we will have PRL ka Amrit Vyakhyaan 2.0, where we will have every month one Vyakhyaan. And this series is continuing now. Today, that is 6th of August, Wednesday, 4 p.m., we have yet another very, very distinguished Vyakhyaan Karta with us, Professor Ajit Kembhavi, who is currently Emeritus Professor at Inter-University Center for Astronomy and Astrophysics. And he is going to talk to us on a very pertinent topic, AI, astronomy, and citizen science. AI, as you all know, that is artificial intelligence, is a buzzword today, and everybody talks about it. But today we will hear from Professor Kembhavi how AI is helping astronomy and helping citizen science doing astronomy. We thank Professor Kembhavi for agreeing to our invitation to be with us today and delivering this 107th PRL ka Amrit Vyakhyaan. I now request my colleague, Professor Pallam Raju, Dean PRL, to kindly introduce Professor Ajit Kembhavi to the audience at the WebEx and also those who have joined us live on the PRL's YouTube channel. Over to you, Professor Pallam Raju.
Thank you, Professor Bharadwaj. It is indeed my great pleasure and honor to introduce our Vyakhyaan Karta, our speaker, 107th PRL ka Amrit Vyakhyaan speaker, Professor Ajit Kembhavi. He is an Professor Emeritus at the Inter-University Center for Astronomy and Astrophysics, IUCA, Pune. He is one of the founders of the IUCA and was a director there until 2015. He was a visiting distinguished professor at IIT Kanpur. He led the Pune Knowledge Cluster, PKC, from 2020 to 2024, which works on projects related to environment, sustainability, health, big data, and AI and capacity building. Professor Kembhavi obtained his PhD from TIFR Mumbai under the guidance of Professor Jayan Narlikar. And he's internationally renowned astronomer and works on various topics such as extragalactic and high energy astrophysics and application of data analytics and AI to astronomy to biology. It's a very vast region, and he has published a large number of research papers and several books in English and Marathi. He is also involved in many national and international collaboration and is one of the key persons responsible for India joining the 30-meter telescope and the LIGO India projects. He has led the Virtual Observatory India projects and International Virtual Observatory Alliance. He has worked at many research centers and universities in many different countries. In the field of data-driven science, Professor Kembhavi led the Virtual Observatory India project for 15 years, which has made important contributions to the data management, analytics, visualization, and development of tools for statistical analysis. He led a big data project supported by the National Knowledge Network. Professor Kembhavi has been a member of the Space Commission of the Government of India and is presently a member of the ISRO's Apex Science Board and the Chandrayaan National Committee. He was vice president of the International Astronomical Union and president Astronomical Society of India and president of the Indian Association of General Relativity and Gravitation. He is a fellow of the Indian Academy of Sciences and the National Academy of Sciences in India. He's going to talk on very exciting, very pertinent, very topical topic, which is AI, astronomy, and citizen science. It's a great pleasure and honor to invite Professor Kembhavi to please make his, give his Vyakhyaan. Professor Kembhavi, over to you, please.
Thank you very much. I'll just first share my presentation.
Yes, please.
Is that okay?
Yes.
All right. So, first of all, I thank Professor Arun Bhardwaj and Professor Pallam Raju for inviting me to give this lecture, which I do with great pleasure. I have always been very fond of PRL, and it was probably one of the first scientific institutes that I visited in India, apart from TIFR, when I was very young as a graduate student. Then recently, just about a week ago, or slightly more than that, we celebrated in Pune the 100th birthday of Professor Chitnis. And, and a lot of people had gathered there, including many of the senior people from ISRO and its associated institutes. And a lot was said about the early days of PRL and how the entire space program started in that one small institute when there were just very few people there, and how it has continued from there ever since and been led by stalwarts who came from PRL originally. So that was a very fine reminder of the important contributions that PRL has made to science and technology in India. So today I'm going to be talking about AI, astronomy, and citizen science. Now, AI, like Professor Bhardwaj said, is a buzzword now, and the entire media is full of the word AI, so that sometimes you feel that you are tired of it. Isn't there anything else that people can talk about? But as it happens, I mean, this is something which everybody gets carried away with, but it is also very, very important because it is making contributions to every aspect of our life. And if we don't watch out, it may also begin to control our lives. But then those are all philosophical questions. And what I'm concerned with today, how AI can help astronomy. So astronomy has always been a data-intensive science, and for times immemorial. So when the ancient Indian sages like Aryabhatta, they looked at the sky, they collected data. So if you look at, they're all mathematicians apart from being astronomers, and you see that they made all these tables for science and cosines and those sort of things, and then they made quantitative predictions using the data that they had. In the 17th century, Kepler, who was then just a young research assistant, was given data on the orbit of planet Mars uh, by his supervisor and his boss, who was Tycho Brahe. Not Tycho Brahe, I'm sorry. Yeah. So and then he analyzed that data and then gave his famous three Kepler's laws of motion, from which later, uh, which helped Newton very much in deriving his theory of gravitation. That gravitation theory was ready to derive important conclusions from it. Now, of course, the quantity of data and the kind of data that we have has changed radically, as I'll very quickly summarize for you. And as the data pours in, we need newer and newer tools. These again have been invented by astronomers for a very long time, and currently astronomers do lead in trying to find newer and newer ways of doing computation efficiently. So when it comes to astronomical data, it is in many different forms. So here, for example, is an image taken with the Hubble Space Telescope. It's a very deep image of a very small part of the sky, and nearly every object that you see here is a galaxy rather than a star. You can see one star, which is pretty bright, but nearly everything else is a galaxy, and every tiny dot is a galaxy. So when you zoom in onto any one of them, you get an object with a fairly complex structure, which has got 10 raised to 11 or so stars in it, maybe more, maybe less. Um, and each one of these objects needs to be studied in detail, which would be an impossible task. But even picking out uh, the variations, objects which show large variations from each other and studying them would require us to study millions of objects, which simply cannot be done in the traditional way. And as I move forward in my talk, I will tell you of some quantitative limitations of the data that we have now, where these things will become more obvious. So now, if instead of looking at an image of the galaxy, I look at a spectrum of the galaxy, then I will get something like this, which is a spectrum of a galaxy NGC 3941. And where does the spectrum come from? It is simply the summed spectra of all the stars in the galaxy. So there are 10 raised to 11 stars roughly, and some stars are old, some are young, some are massive, some are less massive. And then they all emit the radiations. They all have absorption spectra, each one of them. I'll show you one absorption spectrum later, individual absorption spectrum. But then the spectrum passes through the gas and dust in the galaxy, and therefore it is modified. And an astronomer's job is to take a spectrum like this and to unravel from it the content of the galaxy. Right? So therefore, we need to analyze a very large number of such spectra. Now, this is a different kind of spectrum altogether. It is a spectrum of a quasar, so which is essentially a supermassive black hole. Quasars are associated with the centers of galaxies, and then they emit highly energizing radiations, uh, which lead to the formation of emission lines from the gas which surrounds them. So, such a quasar can completely outshine its galaxy, and the physics that we have to deal with is totally different from the physics of the physics of the quasar is completely different from the physics of the galaxy. Now, here are the spectra of individual stars. Even though you didn't see many stars in the picture that I showed you, our galaxy is, of course, full of stars. And all of you are possibly familiar with these kind of spectra. So each row is the spectrum from a single star. The letters, the symbols on the left give what type of stars it is. And then you see the spectrum, the colors of the rainbow here. And then superposed on that are these absorption lines. Now, it is the study of these spectra which tell us about the nature of the star, what is the surface temperature, what is the composition of the material in it, its temperature, its density, and everything. So, all our knowledge of stars come from the study of these spectra. There are completely different kinds of observation. Is that on the left you see the picture of a specific galaxy, and on the right you see the picture with the addition of a compact object there, which is a supernova which has gone off. So these supernovae go off a few times per century in the galaxy, but taken all the galaxies together that you can observe, there are lots and lots of these supernovae going off. And therefore, what you require is a setup which can quickly detect these supernovae so that we can study them further. And then you are led into what is known as time domain astronomy. And a more traditional uh, data from time domain astronomy is the is a variation in the emission from an individual star or an individual quasar. And here you see what is known as a Cepheid variable, which has got a very specific kind of variation. And from the period of the Cepheid variable, we can say what is its luminosity. And therefore, since we measured its observed brightness, we can say what the distance to the object is. And this was one of the great great discoveries which are made in the early part of the 20th century, which led to our understanding of the distance scales in the universe. Now, this is a different kind of data altogether, which is data which comes from a radio telescope. This is the data of a pulsar, again, with which many of you may be familiar. And each one of these, so the pulsar is a rotating neutron star which emits some of its energy in a beam due to its high uh, magnetic field. And then you see pulses coming from it each time the beam crosses your line of sight. And this is again complete. This sort of data has been around for, I think, that well over a decade now. It is the data which comes from an instrument which is known as a integral flux unit. And there, in an IFU, what it does is that, I just look at this picture of the galaxy. So this is a conventional image, except that it is done only at a specific wavelength. So what happens is that using the IFU, one can actually get a spectrum from every pixel of a CCD. So therefore, you've got a spectrum from different parts of the galaxy all at once. And then the result of which is that you get a three-dimensional information about the galaxy. The X and Y dimensions with which we are familiar, which give you an image of the galaxy. But then in the third dimension, which is the wavelength, every slice of the third dimension gives you an image of the galaxy at a different wavelength. And so clearly, you're going to be able to analyze the emissions from the galaxy in great detail like this. Then, the most recent kind of data which has become available to us is gravitational wave data. So, here in the top of the figure, what is shown is that there are these two black holes which are in orbit around each other. Because they are in orbit, they emit gravitational radiation. Because of the emission of the gravitational radiation, the system loses energy and it shrinks. So there's even greater emission, and eventually the system merges together to form a single black hole. Then you see here in the second part of the figure, you can see the wavelength of the gravitational wave which is being emitted here. And as the object spins faster and faster, the frequency increases. And after the merge, the object has got a complex shape, but very quickly it settles down uh, to the form of a single black hole. And what you see to the right of the figure is what is known as the ring down, which was first predicted by Professor C.B. Vishweshwar. Now, this is not a theoretical construct, it is an actual observation, the first observation of a merging of a gravitational wave event made by the two LIGO detectors in the USA. So that has opened a completely new window for studying astronomy, because you must understand that when you've got two objects like this, two black holes going around each other, it is impossible to see them in any part of the electromagnetic spectrum. There is no energy whatsoever emitted electromagnetically. And then when they merge together also, there are no electromagnetic waves emitted. So if you have no gravitational wave detector, you simply could not observe a system like that. So this is a great eye-opener, meaning that even though we believe that we know everything, there are many other things lurking which we'll see over a period of time. So, again, to emphasize the multivalent nature of astronomy, current astronomy, see a picture of the Crab Nebula, where you see it in the radio, in the infrared, visible light, ultraviolet, X-rays, and gamma rays. Right. So all of these taken to have to be understood, and then you get multivalent astronomy. If you look at the sun, most of its emission comes from the ultraviolet, optical, and infrared. It's a very bright object in the radio and in the X-rays and in every part of the electromagnetic spectrum, but the amount of energy emitted there is very limited. So why do we see it so bright in the radio? Simply because of its proximity to us. Now, these other emissions are not important for understanding the structure, the overall structure of the sun. But the situation is completely different for an object like a Crab Nebula, or even more so for an object like a quasar. Because a quasar emits almost equal amounts of energy in every part of the electromagnetic spectrum, unlike the sun. And therefore, unless you have multi-wavelength astronomy, you simply cannot understand the nature of an object like that. And then you take multi-measure astronomy, there's the electromagnetic waves, and you have gravitational waves, and then you get what is known as multi-messenger astronomy. Right. So the very large quantities of data which astronomers have can come from the study of individual objects uh, by individual astronomers, groups of astronomers, or they can come from surveys. And these surveys are extremely important. So you see that here is the Sloan Digital Sky Survey, with which everybody is familiar. It was made with a 2-meter telescope, 2.5-meter telescope, and it has observed very large areas of the sky. And you see, for example, in 2021, there are 933 million detections with 208 million galaxies and 4.8 million spectra, and so on. And and then a lot of all the data is completely public. There are very beautiful ways of accessing the data and even carrying out processing on the computers belonging to the Digital Sky Survey. And then I think that something more than 20,000 papers have emerged from this single project. So you see that there's a great deal of data, but unlike data in other domains, for example, data in the biological domain or in the chemistry domain is far more valuable in the sense that there are many, many industrial applications which can lead to large revenue streams there. And therefore, it is very difficult to access data in those domains. But astronomical data remains free and it is plentiful. You've got petabytes of data, and which is why it is possible for astronomers uh, to convince large software industries that they should support our work because they benefit from the data volumes that we have. Now, this is just a thing on current and future facilities for India. This is highly incomplete because, for example, I have not included the optical telescopes and other things that we have. Uh, just a couple of projects which are doing extremely well. AstroSat, as again all of you know, PRL has made very important contributions to it, and it is observing the X-ray sky, but also at ultraviolet wavelengths, at optical wavelengths, and it has produced a great deal of very useful data. And then there's the GMRT, which is the biggest telescope of its kind in the world. And then we have Aditya L1, which was launched in September 2023 and is already producing extremely good data. And over the next decade, we expect to have access to the TMT. That project is unfortunately passing through many uncertainties. And then we have got the LIGO India project, which is on its way to construction, and then the Square Kilometer Array. And India is an important, very important partner of all these three very major projects. Then, how does one use large data sets scientifically? So, the job of every scientist is to find patterns, correlations, classes, outliers, and meaning in the data. Outliers are very important because if I show you 5,000 galaxies of a certain kind, you may be able to do very useful work. If I double that number, the amount of work is not going to double. But when I study those 5,000 galaxies, if I can find 10 strange galaxies, so then my point of view would change very dramatically. So we need data analytics, which is consists of the domain knowledge. Without domain knowledge, you can't do anything. And there's a great deal of mathematics and statistics. So you'll agree with me that astronomers, by definition, have plenty of all these three requirements. So every astronomer uh, is a very trained data analytics person. Then we do visualization, we do data mining, and what my thing today, effort today is going to tell you about machine learning and deep learning, uh, which make a great deal of contribution these days for the analysis of astronomical data and for the deeper understanding of it. Right. So when you come to the AI universe, it has got lots of familiar names in it. First, there is something which is called machine learning, which came into being in the 1940s and through various ups and downs uh, has come to its present stage. Uh, there were quite a few downs in the sense that people didn't believe in it, and then they stopped working in it. There were no grants, and again it started, and then the thing exploded in the 1980s, 1990s, and but particularly much of the developments that we use routinely now have been done over the last 15 years, and the most the the facilities which are most enthusiastically used now have been developed over the just last 3 years or 4 years. So all of that involves something which is known as deep learning, and I'll explain to you in a few minutes what deep learning actually stands for. Uh, but there's the intersection of the AI universe with data science. But here you see that under deep learning, we have what is known as convolutional neural networks, autoencoders, generative AI, and then there's a whole lot of things which are known as transformers, diffusion, natural language processing, then the LLMs, and large multimodal models. So if I draw a downwards arrow now, then you'll see that convolutional neural networks were developed sometime in 2000. I believe, yeah, in 2030, the important papers were written, and everything I developed over the last 12 years or so. And other very interesting thing is that if you draw a time scale here with the age of people who are familiar with developments, these developments, you will find that when you go down from generative AI onwards, it is mainly the 20 to 25-year-old people who are familiar with it. But my observation over the last couple of years has been that some of these people have developed extremely good expertise in these things. So I routinely work now with people who are 21, 22, 23 years, and they allow you to carry out very, very sophisticated problems. Then examples of machine learning algorithms. So what are these used for? So I'll give you just a couple of examples. The artificial neural networks, the and could use star galaxy classification. We have got X-ray binary classification. Is an X-ray binary is a compact object in the X-ray binary, a neutron star or a black hole? So I again worked with an intern uh, 4 years ago, and he wrote a very nice paper on it, how this kind of classification can be done. And just a couple of months ago, we revisited that problem, and I've been working with people in Ayuka on it. And there are extremely interesting insights which are emerging from it. Meaning that the question always to ask is that I can use AI to carry out classification, but can the AI provide me with insights which I would have very great difficulty in developing without the use of AI? And the project that we are doing is producing extremely simple affirmative answers of this question, something which anybody can understand without being a uh, great expert in deep learning. So let's begin with machine learning and deep learning, and then so let's see. There's a very simple problem of binary classification. Binaries mean these are not astronomical binary systems. They're just two kinds of objects. So each object has got coordinates x1 and x2, which are shown here. And one kind of objects are red lines, other are blue crosses, but neither the color nor the shape is meaning. The only meaning is in the coordinates, and you see that there are two groups of objects. Now, can I develop a general rule using this? This is all the data that is available to me. Can I develop a general rule? So if people give me an n plus 1th object, can I say straight away whether it is blue or whether it is red? Which group does it belong to? And all that I need to do is to draw this boundary here, and I say anything which is to the right of the boundaries of one kind, to the left of the boundaries are the kind. But how do I mathematically define uh, right and left? Is I draw the normal to this line. And then the equation for the line is w dot x plus b is equal to 0. I mean, all are familiar with this equation, right? So here they are just uh, now you see, if I once I have this line equation defined, if I get an extra point, I just put it into, I get w dot x plus b. If it is greater than 0, it is one group. If it is less than 0, it's another group. Clearly, the boundary is not unique. I could change the slope, I could change the position, and so on. And it's also, it's completely obvious. So, what is the great thing that I'm achieving? But let us see how I would do this with machine learning. All that I need is a single neuron. What the neuron does is that it takes inputs. So in the diagram I showed you, there are just two inputs, but I can have, instead of having a two-dimensional space, I can have a 35-dimensional space, for example. Then I need label points, meaning that I got 15 blue points and 15 red points. The numbers don't have to be equal. Now, what I can do is that I pass the coordinates of successively, pass the coordinate of these points as inputs to the neuron. It just adds the thing together, adds a bias term b to it. And then if that is greater than 0, it gives you 1. If it is less than 0, it gives you minus 1. Right? Now, you take arbitrary values for these w's, and then you pass the coordinates, and it will give you an arbitrary number here. You compare that with a true label, because you know it's a training set. So I got a true label. So I compare it with the true label. And what I do is that I go on altering these weights until the answers that I get are right. How do I do that? So you see that here I got w dot x, start with arbitrary values of w, feed it the x values, and see what you get. And you set up an error function. In the error function, TD is the true value, meaning I know whether it is 1 or minus 1. OD is the value that I get. Take the sum of squares and you minimize that sum of squares. And when you do that, you'll get the correct answers. So this has been done here. Right? So again, nothing has been achieved because I could have done this simply looking at the thing. I could have just given you a line straight away. But now consider this problem of a non-linear distribution of points. So what I need to do here is to find this surface which tells us anything above the surface is red, anything below the surface is blue. How do I do this? For the line, I knew what is the equation that I'm going to start with. But here, I don't know what the equation. It can be very complicated. I give you a very simple nonlinear problem. But imagine that there is much greater mixing of the points. But or imagine the thing where I got 100-dimensional space. Right? So then you can imagine how complex the hypersurface is. And I want to solve this problem. How do I solve this problem? It turns out that you cannot really solve it uh, by using a single neuron. And people proved that mathematically, and that set back machine learning by a decade. But then gradually people became cleverer, and they said that first of all, I use a multiple number of neurons, and secondly, between the input neurons and output neurons, I introduce a layer of other neurons. And then everything is connected together. So, how does this, what is the nature of this network? The nature of this network is that it's a feed forward network, meaning that every neuron is connected only to the neurons which come after it, not before it. It is fully connected, meaning that every neuron is connected to every neuron which comes in the immediately next layer. And then you set up the error function. And then it is possible for you to minimize it, okay, and then actually get this surface. So this surface is neither, you neither start with a known equation, nor do you essentially know the equation of the surface after you have completed the problem. But what happens is that the trained network, it has learned what is the distribution of points in this space. So if I give it a new point, it can tell you which group it belongs to. Now, this is an extremely powerful thing because you can show very rigorously mathematically that any function whatsoever uh, can be which has got certain desirable mathematical properties can be described by a single hidden layer like this. And then if you have got some really mathematically conky function, that function can be described by having at most two layers. Right? And so now we come to, I talked of one hidden layer, now I talk of two hidden layers, but then uh, you see that things are getting very complicated now. Why are they getting complicated? Because if every neuron is connected to every neuron next uh, in the next layer, then the number of connections, each of which is represented by a weight, which is a degree of freedom, can become very large. So, I mean, because you can say that, look, it is not very large. There are just a few hundred lines here. But then, as the complexity of the problem increases, then you could need more and more layers and more inputs and more outputs. And therefore, a network like that is known as a deep neural network. And it can become very impossible to arrange this kind of network, to manage this sort of network and to do the minimization. And there something very interesting happened is that their technique was developed by Hinton and others, who in fact Hinton got a Nobel Prize for AI last year. So Hinton and others did it, and then so they developed a technique which is known as back propagation. See, because the situation is that if when you want to get the best possible weights, it becomes extremely painful and unmanageable when you do it in the conventional way, and therefore you need to start towards the end and propagate the derivatives backwards. So that is an extremely important technique, and which was given, I believe, in 2009 as a very beautiful review paper in Nature, which just got everybody working in the deep network area. Now let us see what is the limitations of the multi-layer artificial neural networks that I described. Here is a picture of uh, President Obama. Now, if you actually look at this, excuse me, yeah, I'm giving a talk. Okay. Sorry for the interruption. So, if you look at this, is if you have taken this picture with your CCD camera, there will be many billions of pixels in it. So each pixel would become, if let us suppose that my job is to train a network to recognize all the presidents of the US. If I show it this picture, it is Obama. If I show another picture, it is Trump, and so on. Then for training, what would be the number of inputs? There will be many billions. And so then if you have many billions, and then you've got many billions of hidden uh, uh, neurons in each hidden layer, the network would become completely unmanageable. So therefore, what do? You say that reduce, I reduce the number of uh, pixels here. I just reduce the resolution. But then you see, if I reduce the resolution, my ability to distinguish between different presidents, it goes down. Right? So, which you really want, you want good results, and therefore, what do? You invent a completely new kind of network. Now, this is called convolutional neural network. This was again done. Um, the first thing was in 2013, so it's very recent. So, what does it do? So, you start with an input image. You give the whole image to the network. The network uses a number of filters, meaning that supposing you got just imagine that I got a picture like this, and I take a vertical slit and pass it through the image. What will happen is that as it passes, imagine it passing across a human face, the face of Obama. As it passes across the nose, for example, the intensity will change rapidly because the nose is vertical. But as it passes across the eyebrow, it will not change. So passing a vertical filter tells me about vertical features. Passing a horizontal filter will teach me about horizontal features and so forth. So a network like this has got a very large number of filters. Now, the most important thing to understand is that these filters are themselves trainable, meaning that when I'm using a CNN, I won't go and specify that I need uh, these filters of these kinds. I just say use 200 filters. And it is a deep network. It first uses these filters, then it reduces the size of the image by picking out the most important pixels, and which is known as pooling, and applies this through many different layers of filters, reduces the data to a manageable proportion, and there you use an ANN classification of the kind that I described to you. And when you do that, see, for example, here is a developed network, and you see here that this particular network has been trained to distinguish between a car, a truck, an airplane, a ship, and a horse. And when you are shown a car, the length of the green bar shows you what is the probability of the object being a car. So you see that this particular network is doing a good job. So now I pass from this introduction to the study of galaxy morphology and how we can apply this to galaxy morphology. So I don't have to tell you what's a galaxy. There's just pictures of a Milky Way galaxy here, the center. And the Milky Way galaxy, this is the near infrared image made by panning across the Milky Way. But I still can't see the spiral arms, and which you can see if I go to a different galaxy like M51, which I'm seeing face on, and you can see all the spiral arms. And here there's a much simpler galaxy, which is an elliptical galaxy. So the what you'd like AI to do is to just give it a just an image of a galaxy, and the AI to describe to me that what has it got? Has it got spiral arms? Has it got a bar, ring, this, that, this feature? We are still far from it. But what I want to show you two efforts here in Ayuka for detecting bars and rings in galaxies. So what is a barred galaxy? So you see M51 here at the bottom of the picture. You can see beautiful spiral arms. But if I look at the other one, there are spiral arms, but in addition, there is a clearly linear structure which is present here. And it is present in all these three. These are spiral galaxies. The bottom right is what is known as a lenticular galaxy, which has got a bulge and a disk, but no spiral arms. And you see that each one of them has a bar. A bar is a very important thing because it arises due to dynamical interactions within the galaxy and also because of possible perturbations from other galaxies, other neighboring galaxies. And then once a bar is formed, the material, stars and gas flows from the inside to the outside, and which leads to evolution of the galaxy. So we believe that there are bars in about 40% of the galaxies. But I would like to find bars in many galaxies because then I can do the astrophysics of them. Then here are called galaxies with rings, and you see the bottom left is a very beautiful ring. Bottom right, up upper right again you can see a ring, and on the left upper left you see no ring. So the question is, can I find galaxies with rings? Can I find galaxies with bars? And so there are two papers here written about 5 years apart. One is detection of bars in galaxies using a deep convolutional network, and then other was automated detection of galactic rings from Sloan images. So you see, what we have to do is that we have to define samples of galaxies. So, so you can see that here there are galaxies without bars and rings, then galaxies with bars, and galaxies with rings. Now, what you do is that just like we were trying to distinguish between the different American presidents, now what we do here is that you set up a neural network. Now, one thing which I would like to stress is the fact that there are many, many different uh, tools which are available for doing all these things, and which is why young people can adopt to it very quickly. So, for example, the network architecture, you could write your own network. Now, where there is something called AlexNet, for example, which is available and which is already a predefined network. All that you need to do is to fine tune it to your own requirements, and then you use these things called Keras, etc., which will do all the job for you. So once this is done, you will feed a series of galaxy images to it, and then with known things. So let's say that I have a large number of galaxies which are which have bars, and a large number of galaxies which are no bars. And then I feed both of these. This is labeled training, meaning that I know this is a bar, there's no bar, no bar, no bar, like that. And then once it is trained, what you will do is that you will test the network on a completely independent sample of barred and unbarred galaxies. Right? And so when you do that, you see that there's one problem here, that the training sample, if you actually look at the astronomical literature and try to find tables of barred and unbarred galaxies, but you need the images also, you find that there are just 2,700 to etc. So this is amazing. I mean, because we know millions of galaxies, hundreds of millions of galaxies have been observed, but curated samples which you know that bars are very small. A CNN typically requires 30,000. And how do you do that? How do you get those 30,000? You get them by taking these galaxies, by changing the contrast, by rotating them, and so on and so forth. And that is known as data augmentation. These days, of course, you could do data augmentation in a more sophisticated way. That is by, by what is known as generative AI. You could use a GAN or you could use autoencoders to do this kind of a job. Now, you'll ask me, why can't I, if I can use 2,700 galaxies to produce a sample of 30,000, why can't I use 5 galaxies to produce a sample of 30,000? You are most welcome to use it. But then you will find, if you use all the uh, parameters, you will find that the network is overtrained. Meaning that if you give it these 5 galaxies, it will happily classify them. But a sixth galaxy will not be classified with because the network has trained itself to exactly only detect these 5 galaxies. As the number of galaxies goes up, as the augmented, then you get the augmentation from that, the network gets better trained. So there are many, many pitfalls you have in this problem. So now you see that, uh, just one moment, please. Somnath Ataya, Somnath Ataya. I'm sorry. So you see that here there are barred galaxies which are being passed through different filters, and each filter appears to be quite different. And here are the unbarred galaxies which are being passed through filters. So the network knows it. Now you ask a question: uh, how do you? What is the precision of your work? Meaning that if I give you a trade network and you pass through it 100 uh, barred galaxies and 100 unbarred galaxies, how many will it actually detect? So you'll see here that in this table with the green things, you'll find that it detects bars with a confidence of 86% and a unbarred with a confidence of close to 98%. And the recall is 95%. Okay, meaning that, so what does precision mean? That 86%, supposing I uh, use it to classify barred galaxies, to find barred galaxies, 86% of the galaxies which it declares bars will actually have a bar, but the other 14% will be misclassified, meaning an unbarred galaxy has become a barred galaxy now. And what a recall tells you is that what is the fractional content that is correctly identified. Meaning that if I give it so many galaxies, what fraction does it correctly identify as a barred galaxy? Now, you see that these numbers 86% and 97%. If I did this problem with a young person now, he would vastly improve this number 86% because this was done about 5 years ago when we really did not have enough experience with these kind of matters. Now, if you look at similarly for the ring paper was uh, published last year. So you'll see here that it got a precision of 93% for rings and 99% for non-rings. So the performance is very much better now. So, so you can see that these are new galaxies with rings which have been found. And you can see what beautiful and what varieties of rings. But the question is, can I use the same technique to distinguish between different kinds of rings. Meaning, astronomers have already gone and classified different kinds of rings. Okay, inner rings, outer rings, and then you've got rings, polar rings. All sorts of rings are there, and can you do that? The problem is the fact that enough, you don't have sufficiently large training sample. But we are beginning to discuss how to get over that problem now. And look at this. What is a new thing I can do using this network? Three things. I can give you large sets of galaxies with bars. I can give you large sets of galaxies with rings. But now, by using these two networks in succession, I can produce large samples, large atlases of galaxies which have both a bar and a ring. And such things don't exist at the present time. And now we can develop as large catalogs as you want with it. Now, here comes an important consideration that I've got, uh, I've done this with Sloan data. What about Subaru data? Subaru is also carrying out uh, extensive surveys of galaxies. The problem with Subaru data, no, it's not a problem. The nature of Subaru data is that, first of all, it goes for a magnitude deeper at least. Okay, a magnitude, two magnitude deeper. So you got many, many more galaxies. Second, it has got far better resolution. So my trained network will 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 work there with much less efficiency than it works with Sloan. And how can I use my experience with this training in order to find similar galaxies in the Subaru survey? Technically, that is known as transfer learning, and we are in the process of learning how to do transfer learning. So, quickly, star quasar compact galaxy classification. These are four interns. They are all undergraduates, two from ISO Bhopal, one from IIT Bombay, and one from Engineering College in Pune, who came to work with me on a project, and then they finally published this very beautiful paper. So, you see, the problem is this: either I got bright galaxies here, then I got dim galaxies, and I got dim galaxies. Right. So now you see that you've got on the right, you've got a picture of a star. A star is a point object, but then you see that uh, it appears to be extended because of the point spread function, the finite point spread function. But here are four pictures. Here's a picture of a galaxy, and here are four pictures of stars, and you really cannot distinguish between them. Right? And then if I got a quasar, the thing at the center is a quasar, the thing on the right is a star. I can't distinguish between them. So we took up this problem of trying to distinguish between stars and very faint galaxies 25 years ago. So my long-term collaborators Ajit Philip and I and Yogesh Vardekar and one more visiting student from abroad, we worked on this problem. And at that time, we could only use artificial neural networks because the other facilities did not exist. And then we tried to, the problem with artificial neural networks is that you can't feed them an image. What you need to do is to extract properties of these images and then feed those properties. And we use that pretty well to distinguish between them. But these young people, I said that, look, I will give you the images of, unlimited numbers of images of compact galaxies and stars and quasars and learn to distinguish between them. And so they set up a CNN architecture, and then they did that. And then you see here are the feature maps for different kinds of objects. Meaning when you pass them through the network, what do various features see, and then you see that they got excellent accuracy. So what is the so if you give it a mixture of quasars, stars, and then you give it the compact galaxies, distinguishing between them with high accuracy. The question is, how does it do that? It does that by looking at the very, very faint structures which are available, but which are not discernible to our eye. It uses those faint structures to distinguish between these three kinds of objects. So uh, now this question, how is the network operating? What is it able to, what is it using to give you the distinction when a human astronomer cannot do it? Now, that problem in general, not for astronomy, but for any branch of knowledge, is known as explainable AI, meaning that simply because I give you a network which can solve your problem doesn't mean that you'll be satisfied. You ask, how is the network solving this problem? What are the properties that it is addressing? So, explainable AI is an emerging area that tries to do this, and we are asking the same questions for the problem of distinguishing between neutron star binaries and black hole binaries. Because we have got thousands and thousands of RXT spectra of these objects for a total of 31 black hole binaries and 30 neutron star binaries, 14,000 spectra. Look at all of them. It's impossible for you to distinguish between them, but the network can give us 95% accuracy. So we are getting a lot of insights into what is it that the network is noticing that we can't notice. Very interesting area. Okay, now I come to the last thing, which I'll finish in about 5 7 minutes. Is in a citizen science program. But first, let us see what is the problem to be addressed. We are all professional astronomers. Some of us are professional astronomers. What kind of problem? Look at these features in the galaxies. We have already seen barred galaxies and by galaxies without bars, different classes of rings. So collisional rings, resonance rings, polar rings, and so forth. Right here, you can see beautiful galaxies with dust lanes. So you've got Andromeda, where you can see the dust in the spirals. NGC 891, where you see this beautiful dust lane because of the edge on. And here is NGC 1032, again, which has got, you see that the line of dust that you see, it is not really a dust lane. It's actually dust disk which is rotating around the center. You're seeing it as a lane simply because it is you're looking at it edge on. And then you see that here, peculiar and interacting galaxies. You see the galaxies are interacting and uh, they're just tidal forces which sorry you can see you can see here different shells, ripples, and so on, advanced mergers. Then faint features in galaxies. You've got outer shell, you've got long tails, and so forth. Now the question is, when we have all these features, how do we see them? We see them. Uh, how do we classify these galaxies? It is impossible to do them using AI because we don't have large enough training samples and we don't have sufficient numbers of uh, uh, trained things, sufficiently sophisticated networks. So here when I was associated with the Pune Knowledge Cluster, I started a citizen science program to work on. Uh, so here you see on the left a Sloan image, on the right you see a Subaru image, and then you find that Subaru image, find there's much greater detail in it. So we are working with Subaru data, and what we would like to do is to use citizens to look at a series of Subaru images and try to see and try to delineate, try to label different features in it. So you see that what we have here is, for example, we have developed a web interface. So if you are a registered user of the citizen science program, and then you see this web interface where examples of different galaxies are shown 12 times, and then you see one galaxy after the other. First, you are presented with the image, and then you are going to say, does it have a spiral? Does it have a bar? Is it edge on? Is it an interacting galaxy? Does it have tidal tails and so forth? And you have to say yes or no to each one of them. And then you have got so now the thing is that if I'm not showing these images to trained astronomers. I'm showing them to citizens, meaning that they could be high school students, they could be college students, they could be homemakers, they can be banking professionals, anybody who has got some interest in astronomy. And then they have to see all these features, and then they are going to say what is there. So imagine that I say a very nice barred galaxy. Anybody can say it is there. But very few galaxies are like that. There are always ambiguities. So if a person who is enthusiastic but who has limited experience tells me that a particular galaxy has got a bar, then with what confidence can I accept it? But then instead of relying on one citizen, supposing I give it to a large number of people. Now, if all those people, if the large number of people, they gave answers completely at random, then what would it be? What would be the distribution be? The distribution would be simply the same distribution that you get when you are tossing a coin and getting heads or tails in the binomial distribution. And then with the binomial distribution, because when I toss a coin 1,000 times, I'm not going to get 500 heads and 500 tails. What will happen is that I'll get a distribution of heads and tails. So when I give it to citizens, then if since they are not all doing it at random, they are applying their minds to it. The statistic that I will get will be different from the statistics that I get for just for tossing a random coin. So we had the training session for citizens like this and people who join the program, and then we tell them what to do and start doing it. And the kind of citizen was 1,700. Actually, the number has now gone up to more than 5,000. And then you see the different kinds of people. There are students, there are working professionals, senior citizens, there are others, and so on and so forth. And then you see what happens is that we do this kind of a confidence testing. It is I don't have time to go into the details of it, but this is just gives you the confidence intervals on real data and what it says. What is the conclusion that we come from the analysis, statistical analysis? That 30 to 50 responses are adequate to categorize a feature with 95% accuracy. Now you see, supposing I show a galaxy to a person, ask whether there are spiral arms or not, you expect that the answer will be fairly easy. But I can ask a slightly more difficult question, in which case you need more people. Spiral arms or not, even 20, 25 people is enough. So here we see that 30 to 50 responses are enough. So in this manner, we have collected data on a few 100,000 galaxies. These are not individual galaxies. Individual galaxies may be about 10,000 or so, and other 300,000 galaxies. And we have delineated their features. And the idea is to actually do it for 1 million galaxies, for which a nationwide effort is required. And that requires a lot of support, which I'm trying to find from places. So I'll stop there. Thank you very much.
Uh, Thank you, sir, for a very nice presentation. And I hope there will be a lot of interactions on that. So for that, I request my colleague, Professor Santosh Wadawale, to moderate the question answer session. Santosh.
Yeah. So thank you very much, Professor Kembhavi.
Yeah.
It was a very nice and very comprehensive presentation where you covered starting from what all consists of astronomical data, how vast amount of data we get, and then you went into the basic introduction of how the artificial intelligence it started and how it can be actually applied to astronomical data. You actually gave some concrete example, and then most importantly, how to involve the vast number of people, general common people who are interested in astronomy, of how they can participate. So it was truly enlightening presentation. I hope there are many questions. So I request people on WebEx maybe to raise their hand or start unmute and start asking question. I'm not seeing anybody in chat, but on WebEx people can raise hands.
Santosh, this is Manas. May I go ahead?
I am not. Yeah, I managed to go ahead.
So, Professor Kembhavi, so you talked about using machine learning for the astronomical data application, and it was a really nice example to see how you can classify galaxies. So currently, I'm dealing with a problem such that I'm using this Gaia DR3 data to classify the members which has already gone away from the star clusters.
Yes.
The problem is that when I am using for deeper images, for example, as you said, you used Subar images. For example, if I'm going for a deeper images, which is more sensitive than Gaia, then how to train the sample? Because you are going Fentrol limits,
Yeah.
where your sample may not be, ideally. Your comment on that?
Yeah. So see, this again will not transfer learning. It's a very good question, but it's a technical question. I'll be very happy to speak to you about it offline. If I understand your problem, then I can make some suggestions, or my other colleagues can make some suggestions.
Sure,
Okay?
sir. Sure, sir. Sure.
Yeah.
I'll be in touch with you. Yeah.
Yeah.
Santosh, can I ask one? Santosh.
Sachi, you're trying to say something?
Yeah, I'm asking Santosh
But
whether I
you're,
can ask a question.
yeah,
Okay. So on this identification of different
I
kind of
think
objects.
Sachi, we cannot hear you clearly. Can you be a bit more louder?
Hello. No,
Yeah.
am I audible? Hello.
Yeah, go ahead, Sachi.
Yeah. So you have presented this basically using a lot of data. You have presented classifying different kind of objects, different type of galaxies. The data used are like imaging or kind of data, right? So if you have some slitless spectra or spectra from IFU, is it possible or how difficult it would be to train the machine to characterize all the objects based on temperature, abundance, and everything? Am I audible? Hello.
Yeah, please.
I am
Hello,
audible. Hello.
Can you
So,
repeat the question?
yeah, suppose through morphology or through imaging, you have done some classification by training the machine. You have done some classification, right? From spectroscopy point of view, if you have a spectra of from slitless spectroscopy or spectra from IFUs,
Yes.
how difficult it would be to train the machine to identify and characterize the stars or objects?
Yeah.
Depending on the temperature or abundance of elements.
Yeah. There are two separate things. There are two things there. One is just consider simple classification of spectra. Right. So now you know that, for example, there are 7 main classes, 10 subclasses, and 5 luminosity classes. Right. So several years ago, 3-4 years ago, we wrote a paper on that, and there we had to use a technique which is known as autoencoders. And so where um, once the thing is trained, now if you give me any spectrum, stellar spectrum, I can tell you which class it is. But then, if you want to go further, and that has also been done very well, is that you could actually use AI techniques to even come to some conclusion about the physical parameters which are in there. What is the effective temperature, and so forth. Right. So that has been done, and we had done that some time ago, but we are now trying to generalize those methods. Uh, if you just send me email, I'll send you some references.
Okay, thank you.
Santosh, you are muted.
Oh, sorry. Yeah. So Narendra has raised some. Narendra, can you go ahead and ask?
Yes, sir. Uh, we have tried many. Somehow my voice is echoing. Let me
No,
try
but we
again.
are hearing okay. Narendra, you can go ahead.
Okay. Sir, we have tried many different machine learning methods, but
No,
There's
I'm
an echo.
hearing.
Echo is
okay,
coming.
let me try. Just give me a second. Hello, am I audible?
Yeah, now it is better. Yeah, it is better now. You can ask the question.
Santosh, you are muted again.
Yes, so if I'm audible, so sir, my question was, we tried many different machine learning methods, but somehow the outliers most of our models miss. But in some of your slide, you mentioned that for AI models, it could be possible to even reproduce outlier data points. So can you suggest to me something like how we can target reproducing outlier data, which because their counts is very few. So our models, they are nicely capturing the regular patterns, but they are missing the outliers.
No, 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 no. You see, when you train a model, because most of the objects are the regular objects, that's what you'll learn to think. So my simple idea was the following: that if you if I classify a large number of, there's a somebody has to put off their system here. So if there are a large number of objects which I'm trying to classify, and then a certain number of objects don't get classified properly, okay, then those I would classify as outliers. I would like to see why they are not getting classified properly, right? And then you'll have to develop techniques to find further such objects. See, these are all very interesting questions that you people are asking, but they all require quite a lot of discussion, right? And then there's a lot of work has been done on many of these things. So sometimes when we get a chance, we'll talk.
Okay, thank you.
Yeah.
Santosh, may I go ahead and ask another question?
Yeah, Manas, you can go ahead.
Sir, you talked about to kind of assess the success rate of training sample by confusion matrix. Is there any other statistical method where we can be more be sure what we are classifying or identifying that is actually in a complex system?
Yeah, you
It's
see,
truly
what the confusion matrix tells you, see, there are 3, 4, 5 parameters. There's something called accuracy, there's something called precision, there's something called recall. Okay,
right.
and then these are just gross numbers, right? So they tell you what. See, if I start, see what happened was that we um, we are doing this work on X-ray binaries, and when we published the paper, we had got accuracy. You can say the precision of 85%. Now we are using a sophisticated neural network, and we are getting 95%.
I
Right?
see.
But we are not understanding certain features which are present in these objects. So an expert recommended to us that instead of doing this complicated calculation, you do calculate network, just try a simple linear network. And he predicted that if you do a linear network, instead of getting 95% accuracy, you will get 80% accuracy. Right? And which is exactly what happened. Now the point is that a linear network is easier to understand. Right?
Right.
So we are trying to understand why the linear network is getting 80% accuracy and then extrapolate that knowledge to 95% accuracy. Right? So then another problem that can be of overtraining. Right? Meaning that you will find that as you there are when you look at the performance, as you train it, the performance keeps getting better and better with the training. But then you have to compare that with the performance against a test set, which is independent of training.
Yeah, of
And
course.
there you will find that after some time, uh, the test accuracy starts decreasing. Right? And why does that happen? That is because the network is getting overtrained.
I
So the
see.
weights are adjusting only to the training sample, and they can't say anything beyond that. So there are many different kinds of indicators which are present there. And so these are all of them are gross indicators. And you have to look at the details of the results. Why are some objects giving you good results? Why the other objects are not giving you good results? To develop an overall understanding. Now, for people like us, we are not interested only in the performance of the network. So, see, for example, when the CNN was first invented, so what happens is that in the AI professional community, there are two kinds of things. Okay, there are two important data sets. One is on the NIST data set, which is just numbers 1, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, written by individual people, and you have got tens of thousands of these numbers, right? And the same set is used uh, by everybody. So if you have got a network, you get 91% accuracy. To see whether my network is better or not, I can't use it on some other set. I have to again use it on the NIST set. Similarly, there's another set of things, images, which are 14, 15,000 images of all kinds of arbitrary objects. So when you are in the professional community, when a CNN was developed, it increased the accuracy just by 5%, and that was considered to be totally revolutionary. So all these things depend upon the context. Are you trying to learn how to make the network better, or are you trying to extract maximum astrophysical information?
Yes, yes.
Right. So in the early days, I think it was a very interesting achievement for us uh, to be able to distinguish between different kinds of X-ray binaries. But now the question is, then what? Okay, now that you have done it, can I produce some insight, okay, which I could not have obtained without the use of AI? That is what we are working on.
Yeah. Thank you, sir, for your insightful suggestions and remarks.
Yeah. Professor Kembhavi, there is one question in chat box. Actually, you have already addressed this in your presentation itself, but maybe you can just explain it once more, because the question asks if we are going to use AI to classify a large number of samples, like for example, large billions of images of galaxies, then why citizen science come into picture here if you are already going to use AI? So how the citizen science is coming? That is the question. I think you already addressed it, but then maybe you can still again explain it so that.
Oh yeah, so the citizen science is required for two reasons. One is that to make large data sets available, right? So because unless I have training data set, I can't do anything. And as I told you, if you look at the Bhuta catalog, it has got 2,700 barred galaxies, right? In spite of all the wealth of data that we have. So now the question is, can we produce much larger samples? That is the thing. But then it is not the citizens are not simply working at this low level. Okay, once they help us to collect the data, at the same time they could also help us with the analysis, right? And so which helps in improving their AI insights. So we astronomers gain from producing catalogs, and the citizens gain from learning about them.
Yes. Thank you. So, any other questions from audience, or anybody looked at the questions from YouTube? Because I don't have that. So if there are no more questions, maybe we can thank Professor Kembhavi again, and Manish, maybe you can go ahead.
Yeah, thanks, Santosh. So friends, it is an honor and to propose vote of thanks for today's Vyakhyaan. So first of all, on behalf of Director PRL and entire PRL family, I would like to thank today's speaker, Professor Kembhavi, for sharing his knowledge and wisdom with us on this very special and kind of, you can say, the emerging topic of AI and its applications in astronomy and as well as citizen science. We know, given the fact that astronomical data is exponentially increasing day by day in public domain, it was truly a very insightful Vyakhyaan on AI applications and deep learning applications in astronomy. So I'm sure as we discuss a lot, as I and most of our colleagues and participants who have joined us for YouTube or this platform must have learned a lot. Sir, once again, we thank you for your valuable time. Thank you, sir. Thank you very much for your time.
Thank you very much. It's been a great pleasure for me to give this talk. Thank you.
Yeah. So next, I would like to thank our director, Professor Anil Bharadwaj, and Professor Pallam Raju sir for their constant guidance and support for continuing this Vyakhyaan series. as well as Vyakhyaan committee members for their efforts for this series to keep going. So, and our special thanks to all the participants and viewers who have joined us through YouTube platforms. Thank you again for your time. With this, we come to the very end of today's chapter of PRL ka Amrut Vyakhyaan. See you again next month with another 8 interesting Vyakhyaan. Please visit our social media platforms for upcoming events at PRLA. Thank you. Have a great evening. Thank you.
Thank you.
Thank you, sir.
Thank you, sir.